Today we are going to discuss about the Latin scale design in experimental design. We have already discussed some experimental design like complete randomized design, complete randomized block design. So we have discussed some special terms with that, with sampling, with some missing values, with more than one missing value. Likewise, we have discussed various sources of variance. So due to that part, the part we have already discussed, you will realize we can improve the sources of explainable variation and unexplainable variation. So when we are adding more information in our model, we can explain the variation of our dependent variable anyhow. But with the technique we discussed with the sampling matter inside of the design, we have improved the unexplainable variation part. Then when we are increasing the blocks rather than the treatment, we have increased the explainable variable. So far we have discussed the effect of treatment, replications, and blocks. We have considered some replications as blocks. So we have already discussed those three things: replications, the variation of replications, treatments, and the blocks. So I think you have well aware about those things. Now we are going to move for another step under the Latin scale design. Yes, let's see what I mean by the Latin scale design. The treatments in the randomized block design are randomly assigned to blocks, such that each treatment must occur in each block rather than assigning them at random over an entire set of experimental units as in CRD. There are only two factors, blocks and treatment effects, which are taken into account, and the total number of experimental units needed for complete replications are BV, and B and V are number of blocks and treatment respectively. Okay, take 2 minutes and read the slide again and try to understand what it says. Yeah, that story is still about the complete block design. Then they have remembered again what is the improvement in block design rather than the complete randomized design, because we have to assign each treatment in every block. So in the CRD model, we assign each treatment in random manner. But when we are introducing a block into that model, we have to replicate each treatment under the every block in the experiment. So that is still say about that improvement. Okay, then what means in here, if there are three factors, suppose that B, V, and K levels of each factor, then they have introduced three factors. So B, V, and K are representing the levels of each factor. Then total number of experimental units needed for a complete replications are B, V, K. So I think you will remember when we are calculating the degrees of freedom for the total sum of square, we have considered all observations in the experiment. So as a simple technique to calculate the observed value, we have multiplied the amount of our treatment replications and other factors we are considering. When we are considering sample, we have calculated the treatment amount by the replication amount and by the samples, how the sample amount. So likewise, it has given an idea here also when we are considering three factors by considering B, V, and K amount levels for each factor. we are taking the multiplication in between BVK to calculate the total number of experiment units. I will use the highlighter. Total number of experimental units for replications BVK. This increases the cost of experimentation and the required number of experimental units over BR. So that increases the cost of experimentation and required number of experimental units over BRD. So rather than the complete randomized block design, these have more experimental cost as well as that required more experimental units. So that is one difference in between CRD and LSD. I am using LSD stand for Latin square design. In LSD, the experimental material is divided to row and column. So here we are specially using two terms called columns and rows. So after that, we are discussing about effects like column effect and row effect. Each having the same number of experimental units, which is equal to the number of treatments. So those all are having same number of experimental units, which is equal to the number of treatments. The treatments are allocated to rows and columns such that each treatment occurs once and only once. So let's see this again. Columns such that each treatment occurs once and only once in each row and in each column. So one observation may be coming under the one column with respect to the one row. So in one row, there shouldn't be same two observations. So with respect to the columns, in one column, there shouldn't be equal number of replications in column wise. So you will realize what it says in later when we are showing you an figure about this case. In order to allocate the treatment to the experimental units in rows and columns, we take help from Latin square. So for the special case like this, when you're considering the column effect, row effect, and the other treatment effect in here, we have considering about the Latin square design. Then what is another speciality in here? There should be equal the columns, rows and columns each having the same number of experimental units, which is equal to the number of treatments. So this condition especially should be fulfilled to use this Latin square design in our experimental design. Okay, now you can see a graphical mode of Latin square. Okay, let's see. A Latin square of order P is an arrangement of P symbols in P square cells arranged in P rows and P columns. So now you can realize, then if we consider the order P, there should be P rows and P columns. Then there should be same amount of columns and rows. Then the treatment also in that amount, such that each symbol occurs once and only once in each row and each column. That sentences have mentioned again. Then I will show you what it says. Now I am going to color the letter A. I have used green color for letter A. Then can you tell me whether are there any two observations with respect to columns and rows? Then if it has repeated in the same column, you can say me what is that column. If it has repeated in the same row, you can tell me it has repeated in this row or this column. Okay, try to start, and if there are no repetition, you can state that in the chat box. Likewise, you can consider about other all things also. Then here treatments are, there are 4 treatments, A, B, C, D. Then you can see about those 4 whether that has occurred in same row twice or a same column twice or more than twice. Then if it is in that way, you can mention. Okay, try to start to find that rule has come fulfilled in this problem or not. What we were discussing about this one. Each symbol occurs once and only once in each row and in each column. That condition is a must for a Latin square design. Okay, I think you will not find any violated situations for this condition. So all cases are fulfilled in this way. So when you see letter A, it's happened in column 1 and row 1 here, column 2 and row 4 here, column 3 and row 3 here, column 4 and row 2 here. Then likewise, other letters are also appeared in once in each column and each row. For example, to write a Latin square of order 4, choose 4 symbols A, B, C, D. These letters are Latin letters which are used as symbols. Write them in the way such that each of the letter out of A, B, C, D occurs once and only once in each row and column. For example, it has distributed in this way. If you have any question, you can ask. If you have any question, you can put it in the chat box. I will continue this explanation. This is a Latin square. We considered first the following example to illustrate how a Latin square is used to allocate the treatments and in getting the responses. So here you are having an example. Suppose different brands of petrol. So it's an important point in these days. Suppose different brands of petrol are to be compared with respect to the mileage per liter achieved in motor cars. So they have used 4 petrols. They are checking mileage per liter by using some different motor cars. Important factors responsible for the variation in mileage are, they have considered 2 things as an important factors, as some important factors of that variation in their mileage of those fuels or petrol. The difference between individual cars, because they have used 4 motor cars, so they have considered the differences in between those 4 motor cars. The next point is the differences in driving habit of drivers. Then they have considered the one factor as the driving habit of drivers. So they have considered about these 2 things. Then what's their treatment? Their treatment is 4 different petrols. Okay, then they have designed a Latin square design to sort out this problem. So you can find this kind of example in your real life and you can apply this kind of techniques. Then not only for this course, for your dissertations also you can use these things. For your other research also you can use these techniques. We have 3 factors: cars, we have 3 factors: cars, drivers and petrol brand. Suppose we have 4 types of car denoted as 1, 2, 3, 4. For drivers that are represented by simple A, simple B, simple C and simple D. 4 brands of petrol are identified as capital A, capital B, capital C and capital D. Now you know there are 3 classifications in our whole design. Now the complete replications will be required 4 times 4 times 4, 64, the number of experiments. We choose only 16 experiments. To choose such 60 experiments, we take the help of Latin square. Suppose we choose the Latin square, following Latin square. So then what this says? What mean by this thing? suppose you have taken first car. Then what you should apply? You should use the first car with these 4 drivers. Then you should use one with first car with driver A, driver B, driver C, driver D. Then you need to use first car with driver A with petrol A. Then again you need to use car A, car 1 with driver A with petrol B. Then again car 1 with drivers A with fuel C. Then 1 with driver A and fuel D. Likewise, you have to do these 4 again into B also. Car 1, driver B with petrol A. Car 1, driver B with petrol B. Likewise, then how many observations you will have in here? 4 times 4. You will have 1, 2, 3, 4, 4 times. So you will have 16 only for the first car. Then if
Madam,
you have to, sorry?
Can you explain it again?
Okay.
Can you explain it again?
Yeah, sure. Then what I stated, suppose now you are going to do something, some technique which are not applicable, which are not coming under the experimental design. You are going to use some separate thing. Then what is the way you are taking in there? You have to test the effect of car 1 with these all 4 drivers and with these all 4 petrols. Yes, then these column representing the drivers. Sorry, this is about motor cars. So there were 4 drivers that was represented by the simple A, simple B, simple D, and simple C. Then the petrol type. Okay. To test the effect of first car, I should use first car with driver 1 and with these 4 fuels. Then I will have different 4 results when I'm using first car with first driver and with these 4 fuels. I will have 4 different observations. Then did you realize that one? If you have any question, you can put it in the chat box or you can ask it by unmuting your microphones. Then I can use the first car with driver B and with these 4 fuel types. Then I will have 4 different answers. or I will have 4 observations with respect to 4 different applications. Then I can use first car with driver C and with this all fuel consumptions. First car with driver D and again with these 4 fuel types. Okay, then you will realize we can do the same thing for second car either. We can apply second car with first driver and with these 4 fuel types. Then give me an answer, put your answer in the chat box. How many observations we will have at the end? How many different applications we have? For one car type, we are having 4 drivers. One car type, we are having 4 drivers. Again, we are having, then when we take multiplication of these things, we are having 4 observations. For these 4 observations also, we are having again 4 applications with 4 type of petrol. So again, we can multiply this by 4. Then what is the answer I have? It is 16. 16 observations I will have only for this first car model. Then for the second car, how many observations I will have? Now you can make counts for the second car and third car and fourth car. Put your answers in the chat box. What is the answer you will have? Then I have already done the calculations for the first car and I introduced for the second car either. So you can complete. You can mention me how many different applications you will have in this way. I have already teach you that, but you need to realize how it has come. Then how many different applications you will have as all together for this case? All together, how many observations we have? Yes, altogether we will have 64. I received answers from one student. What about others? If we follow these steps, finally we will have 64 observations. We will have 16 observations for these all 4 steps. Altogether there may be 64. Okay, then what we have done in here, we choose only 16 observations. Only 16 experiment to sort out the same problem by using experimental design. So even though we will have 64 types of different observations, we have all included those all together in this 16 experiment. Let's see how that has happened. To choose such 16 experiments, we take the help of Latinistica. Suppose we choose the following Latinistica. Then for this case, we can put our observations in this way. Okay, I will. Okay, let's see. We have represented these things along with our rows. So I will put 1, 2, 3, 4. These red color 4 numbers are representing our car type. This green color simple ABCD represent driver's effect. A, B, C, D. Then the middle part are representing the brands of petrol, the capital A, B, C, D. Now, can you tell me whether we have addressed these all applications we have considered under the 64 applications in the previous time? Can you tell me whether we have applied those all in here or we have ignored anything? Yeah, in this slide that explain about the differences between RBD and LSD and what are the importance of these things. So you can surely read that one. The analysis of data in Latinistica design is conditional in the sense of depends on which Latinistica is used for allocating the treatment. If the Latinistica change, the conclusions may be changed. So as we discussed here, we will have some different applications. So this Latinistica application is somewhat different with this sheet. Then if you consider about first row, A, B, C, D is the order of there, but it is somewhat different here. So in these 2 applications, you will have 2 different two different results. So that is the important of Latinistica design. We know that Latinistica play an important role and Latinistica design. So first we study more about these Latinistica before describing analysis of variance. Okay, now you are going to identify the model. So in every experimental design case, we need to mention the model. What is the model you have identified? Because in the practical situations, you will have only the case. You should identify what is the suitable case to handle that kind of situation. So if you have identified a correct model, you should represent it. What's the model you are going to estimate using the linear model of that design. So the linear model for the Latinistica design is in this way: mu plus alpha I, beta j, and tau k. alpha, beta, and tau are representing. Alpha is representing the effect of rows, beta is representing the effect of column, and row is here it has given row. Row is representing the tau here. Anyway, that is representing the treatment. So ith amount of rows, jth amount of column, and kth column of treatment. So according to our given case, as it mentioned in here, rows are representing the drivers, cars are represented by the columns, and petrels are represented by the treatments. I think now you have realized that those things. And the excellent are random errors which are identically and independently distributed. Identically and independently normally distributed. That has a normal distribution, it says by this one. Then the null hypothesis of our all statistics are in here. So rows, columns, and treatment. We need to mention our hypothesis separately for the rows, columns, and treatment. We are going to estimate whether our responses are having effect of rows, effect of columns, and effect of treatment. So if we have confirmed that we have an effect of rows, that says we are having an effect of, we have some different effects from the drivers. If we have, I'm giving conclusions according to this classification because in the previous case I have used this in different way, but you can base these applications, rows as drivers and columns as cars. Then if we have confirmed with, if we have rejected the null hypothesis of OC, that represents we have an effect of column. That means there are differences in between car type and the T as well. If we have rejected the null hypothesis of T, and if we have taken the alternative one, that says there is a differences between efficiency in mileage in 4 type of petrol. So that is the things we can say. Now we are going to make an estimation. Okay, you can take these equations in your own. Yes, this is the ANOVA table. Then I think this should be changed. This is amount of rows. Then you can use IJ for these all notations, but we are having the same amount, so it doesn't matter to use in this way also. Then this is V square minus 1 for the error term. We can use V minus 1, V minus 2, and multiplication of those two. Then how you will get the F value for rows? You should divide mean square for the rows by the mean square for error. Then you will find the calculated F. Then for the column, you should divide MSC by the MSE. For the treatment, you should divide MST by the MSE. I think you will have no any problem of that. Now I am going to give you an example. Performance of 4 food rations on body weight gain and cattle investigated. So what are the things you are going to test? 4 food rations on body weight. That is our response variable. Food rations on body weight gain on cattle. 4 farms were used. 4 farms were used in experiment and 4 bulls. Now we have identified our 3 cases. The treatment is 4 foods and we have considered 4 farms and 4 bulls of 4 different age groups. Bulls are coming from 4 different age groups. were used at each farm. Note that age group was same in all farms. Farms, there were total of 16 bulls used in the experiment. The body weight gain kilogram recorded after certain time period in the is given below. So this is weight class 1, weight class 3, weight class 2, 3 and 4. These are the farms. So they have considered uh, same age cattle in different form of farms, and they have used same uh, body weight at the very beginning. Then after giving this treatment of 4 foods ABCD, at the end they have considered again whether these cattle are having difference from these foods or not. Okay, now you can apply this one, and you can find out the answers. Okay, you can take this data set also into your note. If you have any question, you can ask. If you have any question, you can ask. Otherwise, I have to stand from the sheet for a few minutes.